Hey everyone, welcome back to HM Learnings. I am Harshita, the creator of HM Learnings, where students come to clear their concept and to get the study material. Make sure you subscribe our channel. So today we are back with the next video of the respiratory physiology, that is about the Fick law. And you can also see that we have upgraded the upload of our channels. So now you can see me also while seeing the session, while seeing the video, because we have done this so that we can make it more engaging and interactive, and we want it to be engaging from your side, so from your side also. So you can do it by commenting in the comment section about your suggestions, about your feedback, and also let us know that if you want the live sessions, live question answer sessions with us. So please like, share and subscribe our channel. So we are going to talk about the Fick law. This video is a continuation of the previous video. So you have, if you haven't watched the previous video, I recommend you to watch it. You can see the link in the link in the I button and the description box. So in the previous video, we have talked about what is diffusion, what is the net direction of diffusion, what is the force of diffusion, and we have ended the previous video on the questions like what is the rate of diffusion, what determines the rate of the diffusion, and when will the diffusion stop. So these questions can be answered by the Fick law, which is what we are going to see today. So before jumping to the Fick law, we will first see what is diffusion rate. So this slide shows you a hypothetical example in which you can see. So I'll use a laser pointer here. So this black one is showing a barrier. Okay, so this barrier is separating the two air-filled compartments, and these air-filled compartments is having a mixture of air, and one of the air in them is oxygen. So there are oxygen molecules on side 1 and oxygen molecules on side 2 showed in red dots. So you can see that there is a difference in the concentration of the oxygen molecules on side 1 and side 2. So let us take the example that suppose the concentration of the oxygen molecule on the side side 1 is 40 moles, which is present in 100 ml of air, and other side also you say that there is 100 ml of air. In that you say that the 20 moles of oxygen are present. So you can take the value in the moles, or you can take the value in the gram, or in the molecules also. It depends upon the mole concept. So you can take either of them, they are interchangeable. Now, so from this you can see that the number of oxygen molecules, or the number of the moles of oxygen, is actually higher on the side 1 as compared to the side 2. So definitely the net direction of diffusion will be from side 1 to side 2. So there will be more diffusion of oxygen molecules from side 1 to side 2 as compared to side 2 to side 1. So this shows a net direction of diffusion. Now there is another thing which is called as a concentration gradient. So concentration gradient means that there is a difference in the concentration, which we can see here also. So how can you calculate the concentration difference? You can actually subtract the area which is having lesser concentration from the area which is having higher concentration. So here it will be C1 minus C2. So that is 40 moles minus 20 moles gives you 20 moles. So the concentration difference between these two areas is 20 moles of oxygen. So now you know that the side 1 is having 40 and side 2 is having 20 moles. So now the diffusion of the oxygen molecules has started, and suppose 10 moles have shifted from diffused from side 1 to side A. So now you have stopped the diffusion. Okay, so here what happens that now if you see, the moles of oxygen will be at this point will be 30 moles left on the side 1 and about 30 moles on side 2 is there. So at this time point, if you calculate the concentration gradient, it will be 30 minus 30, that is 0. This is the time at which the diffusion will stop. So what is the time, or what is the factor which is going to decide that the diffusion will stop or not, is basically your concentration gradient between the two barriers, so between the two sides across the diffusion, across which the diffusion is happening. So basically if that concentration gradient becomes 0, the diffusion will ultimately stop. So this is the answer. And now how many oxygen molecules or moles have actually shifted? almost 10 moles have shifted, because after shifting of the 10 moles, what has happened that the concentration gradient or the concentration on both the sides become the same, and therefore the concentration gradient becomes 0. So further net diffusion is not happening. Mind you that the diffusion is still happening. The molecules are in constant motion, so they will be moving from side 1 to side 2 and side 2 to side 1. But the net diffusion now is 0 because the concentration gradient is 0. So same number of moles of oxygen is moving from side 1 to side 2. At the same time, the same number of moles of oxygen are moving from side 2 to side 1. Therefore, the net diffusion rate is equal to 0 when the concentration gradient is 0. Now, suppose this 10 moles which have transferred from side 1 to side 2 has taken 10 seconds. Okay, so it has taken 10 seconds to diffuse from side 1 to side 2. So how can you calculate the diffusion rate, or if I say the speed of the diffusion, or I say flow? So it is defined as 10 moles have transferred in 10 seconds. So that means 1 mole per second has transferred from side 1 to side 2. This is what is called as the diffusion rate, which is written as moles per second. Okay, so this is what is the definition of the diffusion rate. This is how we define the diffusion rate. Now suppose this barrier is having an area of 100 meters square, okay, across which the diffusion is happening. So that means 1 mole per second is diffusing from side 1 to side 2 across a barrier of 100 meters square of area. Now, if you want to say that what is the diffusion rate of molecules per second per meter square of the area, you are going to do what? You will divide 1 mole 1 second with 100 meters square, and this gives you 0.01 mole per second meter square. So that means 0.01 mole per second per meter square of diffusion barrier is moving from side 1 to side 2, and this is defined as the flux. So flux is moles per second into meter square. So this is a difference between a flow and a flux. So flux is actually talking about per unit meter square or area of the barrier across which the diffusion is happening. So the Fick's law is actually defining the flux. Okay, so according to Fick's law, the flux is directly proportional to the concentration gradient. So flux from side 1 to side 2 is directly proportional to the concentration on side 1, and flux from side 2 to 1 is directly proportional to concentration gradient of side 2. So the net flux will be directly proportional to the concentration difference between these two sides, which is being written here. Now, how does this proportionality constant is being removed? This is being removed by adding the constant as permeability coefficient. So what does this permeability coefficient includes? Okay, so what is diffusing? Gas is diffusing. Across which is diffusing? Barrier is diffusing. It is passing the barrier to enter the other side of the area. So basically it includes the barrier, it includes the properties of gas, it includes the property of barrier, and it is treated as a constant here. So we see that the flux is defined as permeability coefficient, which has unit of centimeter per second, into the concentration gradient. Flux unit we have already discussed. Flow is defined as, I erase this thing. Flow is defined as flux into area, and the unit is moles per second. A is the area of the barrier. Now, permeability coefficient is being defined as diffusion coefficient, which depends upon the properties of gas, which will be discussed later, into the partition coefficient divided by the membrane thickness. Membrane thickness is basically how thick is your barrier, is what they meant here by membrane thickness. What is partition coefficient? Partition coefficient is basically telling you that if you are having the same ml, same amount, same ml of the two solvents which are different, which are not mixable with each other. Suppose one is your organic solvent, another one is water. So we know that these are basically not soluble in these are not soluble with each other. So what you have done, you have added the solute, the same solute in this, and then you have seen that what is the concentration of the solute in the organic solvent and what is the concentration of the solute in the water and you drive the ratio. This is the permeability coefficient. So this is telling that if the permeability coefficient is high, this basically means that this particular solute is more soluble in the hydrophobic organic solvents as compared to the water. So most of the gases, they are having higher partition coefficient because they are more soluble in the lipid as compared to the water. So this is considering the properties of the gas and the barrier. So in the case of the respiratory physiology, what is important to remember that this is not the Fick's law which is used there. So they have derived a Fick's law of respiratory physiology from this Fick's law, and now we shift to understand how the Fick's law is being used in the respiratory physiology. So instead of diffusion rate flow, which is there moles per second, as we have seen in the previous slide, instead of measuring the diffusion rate as such, they are actually measuring what is the volume of gas which has diffused across barrier per unit time, which is written as like this. Okay, so not moles, but actually the volume of the gas which is being diffused per unit time across a barrier is what measured in the respiratory physiology. And here the volume is directly proportional. The net volume which has diffused per unit time is directly proportional to the concentration gradient, and concentration gradient can be replaced by the partial pressure gradient. As we already know, concentration is directly proportional to the partial pressure is directly proportional to the concentration gradient. Now this constant is being replaced by this proportionality constant is replaced by the diffusing capacity of the lung. What is diffusing capacity of lung? It is definitely going to consider the property of the gas, of the barrier, and how the gas and the barrier is going to interact with each other, and we will be discuss about this in the coming slides. Okay, so here this is what the overall Fick's law which is used in the respiratory physiology. Now before moving ahead, we need to understand that moles, which has been determined earlier, is something which is a constant volume with constant parameter quantity, which is not changed by volume, which is not changed by the pressure and the temperature, but volume of the gas is something which is changed by pressure, which is changed by temperature. Therefore, at different temperature, different pressure, the volume of the gas is going to be different. So volume of oxygen inside the body will be different. Volume of oxygen outside the body will be different. So there are conversion methods which are used for converting the volumes in between these things. And there is a we can have a total separate video for that. So if you want to know about STPD and ATPS and STPD and DTPS, their conversions, please write down in the comment section. We will have a video on it. This is important for the practical purposes. Now, after knowing this, we will switch on to understand what is diffusing capacity. So till now we have seen that there is a dry homogeneous barrier, but in the case of the lung, it is not like that. You are going to have almost 12 barriers which is present between what? Between your alveoli, between the air which is present in the alveoli, and between the hemoglobin which is present in the RBC. So there are almost 12 barriers between them, and every barrier is having a kind of a different diffusing capacity, because every barrier is having different feature. It is having different the barrier is having different area, the barrier is having different thickness. Okay, also the way with that barrier how the gas interacts is also going to be a different. Okay, so gas and barrier interaction is also going to be different, and how much gas is soluble in that particular barrier is also going to be different. So for 12 different barriers, you are having 12 different diffusing capacity which needs to be considered before calculating, or which needs to be put in the formula for knowing that how much volume of oxygen has diffused across these 12 barriers per unit time from alveolar wall, from alveoli to the blood plasma or to the hemoglobin. So for that, the diffusing capacity includes what? It includes the gas, about the gas. So what does the properties which is being there? The molecular weight of the gas. So more the molecular weight, it will be taken more time for the gas to diffuse. So the more molecular diffusion of the gas is directly or inversely proportional to the root of molecular weight of the gas. More time will be taken by a gas to diffuse across the barrier if the molecular weight is more. Now, what about the solubility? So you are having the oxygen molecule here, okay, in the alveoli. Now it has to go and it has to come here in the blood plasma. There is a barrier between them. So now it has to go there in this barrier, then there, then finally comes here. So first it has to dissolve in here. So how much oxygen is going to dissolve in this barrier will depend upon the solubility of oxygen in that barrier. That can be calculated by what? That can be calculated by the Henry's law, which we have already discussed. Again, how much oxygen will come in this barrier will depend upon how much it is going to be soluble in this at a particular PO2. So that is also going to be explained by Henry's law. So solubility of the gas is important. More soluble the gas, more it can diffuse from one side to other side, and therefore it is directly proportional to the diffusion rate. So two properties of the gas which determines the diffusion rate is the molecular weight of the gas and the solubility of that gas in the 12 different barriers which are present between the alveoli and the RBC and the hemoglobin. Okay, so now we talk about the diffusion coefficient of the gas. So the solubility divided by the molecular weight forms the diffusion coefficient of a gas. Okay, so higher the diffusion coefficient, higher will be the diffusion rate, and different gases is going to have a different diffusion coefficient. So suppose if you see that the oxygen diffusion, you have just assumed that the oxygen, how much oxygen is diffusible in the body fluids is 1. Okay, so then the relative, like compared to oxygen, what is the diffusion coefficient of other gases? So like for carbon dioxide is 20.3. So that means carbon dioxide is 20 times more easily diffusible than the oxygen. So if you remember that we talked about the solubility coefficient also. So solubility coefficient depends upon how the solute interacts with the solvent. So here also the solute is your gas and the solvent is your barrier. So oxygen is interacting less with the barrier as compared to the carbon dioxide. So as a result, the solubility of a carbon dioxide in that barrier is more than the oxygen solubility in the same barrier. And as a result, it will be more, the carbon dioxide is going to be more diffusible as compared to the oxygen across the same barrier. So that is how carbon dioxide is more diffusible than the oxygen. And you see other gases, carbon monoxide, nitrogen, helium, they are actually less diffusible as compared to the oxygen. And this is very important when we talk about the perfusion limited gases and the diffusion limited gases. So you should remember this slide for those discussions. Okay, now we move on to the properties of the barrier. One property is the area. So if you're having a barrier which is having an area of 110 meters square and you're having a barrier which is having 100 meters square. So definitely, because the area is more available for the same time for the gas to diffuse across that barrier, it will be more diffusion. The diffusion rate will be more for the barrier which is having higher area. Okay, thickness. More the thickness of the barrier, lesser, more the thickness, more time it will taken by the gas to diffuse. As a result, the diffusion rate will be less. So this is what is shown here. If the barrier is thick, it will be taken more time to diffuse. If the barrier is less thick, it will be taken less time to diffuse. So diffusion rate will be higher. So this is how you define the properties of the barrier. Then comes the proportionality constant, which is basically how the gas is going to interact with the barrier, different from 12 different barriers. And ultimately, what is your Fick's law which is being derived? The net volume of oxygen which is diffusing per unit time across the barrier will be equal to the proportionality constant into the area of the membrane into solubility of the gas in that barrier divided by the thickness of the barrier into the molecular weight, root of the molecular weight of the gas into my partial pressure gradient. This defines the Fick's law. So if there is increase in the area of the membrane, what will happen? There will be increase in the diffusion rate. Okay, if there is increase in the solubility, there will be increase in the diffusion rate. If there is increase in the membrane thickness, decrease in the diffusion rate. If there is increase in the molecular weight, decrease in the diffusion rate. If there is increase in the pressure gradient or the concentration gradient, increase in the diffusion rate. So this is how we come to the end of this video. These are the two references you can look upon if you want to understand it better. And in the comment section, please let me know what is mole, what is molecular weight, and what is the gram, gram weight, grams. How can you convert it into grams of the gas also? Okay, this is important to understand, that how you derive mole, how you derive molecular weight of the gas, and of course the number of molecules of the gas. Okay, so if you like this video, please like, share and subscribe. Comment down your suggestions for upcoming video. Till then, keep learning.